You know, for almost all of human history, when we looked up at the sky, we were just spectators. We could track asteroids, figure out their speed, their direction, and if one was headed our way, well, we could only watch and wait. But that has all changed. So let's get into this absolutely incredible story of how humanity decided to fight back.
Just let that sink in for a second. I mean, really think about it. For the very first time, we didn't just observe, we acted. We reached out millions of kilometers into the void and literally changed the destiny of an asteroid. This is a huge deal.
And that's the big question, isn't it? Why go to all this trouble? Why spend all this time and money to build a spacecraft just to smash it into a rock? Well, to answer that, we have to talk about the massive threat that's been hanging over our planet since the beginning.
To really understand why we're building a planetary defense system, we've got to look back, way back, to what happened the last time Earth's defenses failed, long before any of us were here to see it.
Yep, we're talking 65 million years ago. This is the date of probably the most famous disaster in our planet's history. An asteroid, 10 kilometers wide, that's about the size of Mount Everest, just slammed right into the Earth.
The devastation was, well, it was absolute. It set off tsunamis, massive firestorms, and kicked up so much dust it created a global winter that changed the climate for years. It was a true extinction-level event. It wiped the dinosaurs clean off the map. And the most important thing to remember is, it could happen again.
And listen, this isn't just some ancient history lesson. Right now, as we speak, NASA is tracking over 26,000 of what they call near-Earth asteroids. These are space rocks whose orbits bring them a little too close to home for comfort. Now, thankfully, none are on a collision course today, but orbits can and do change. And here's the scary part. Out of those thousands, 888 of them are bigger than a kilometer. That's the size that can cause a global catastrophe.
Think about that for a second. Not one, not 10, 1,000 nuclear bombs all going off at once. When you hear a number like that, suddenly the idea of a planetary defense plan doesn't just sound smart, it sounds absolutely essential for our survival.
So when you're faced with that kind of existential threat, what do? Well, scientists decided to move from just watching to actually doing something. They came up with a theory, a really bold new way to protect our world.
It's called the Kinetic Impactor technique, and the idea is actually pretty simple. You hit the asteroid that's threatening you with something, in this case a spacecraft, to knock it off course. It's kind of like a game of cosmic billiards, you know? You just have to tap the ball at the right angle to avoid sinking it in the wrong pocket. And here's the beautiful physics of why this can actually work. Out there in the vacuum of space, there's no air, no friction, nothing to slow you down. An object in motion just keeps on going. So a tiny, precise push, given millions of kilometers away, can be just enough to alter an asteroid's path, so that over time, it misses Earth completely.
So this all builds into this really elegant four-step plan. First, you've got to identify the threat. Then, you launch your interceptor. Third, you collide with the target. And finally, if all goes well, you deflect it. The theory was rock solid, but it had one small problem. It had never actually been tested in the real world.
And that, my friends, brings us to the mission that put this whole idea to the ultimate test, DART, which stands for the Double Asteroid Redirection Test. This was humanity's first practice run for saving the world. So DART launched in late 2021 and spent almost a full year traveling 10 million kilometers through deep space. Its target was a small asteroid moonlet named Dimorphos. This entire long journey was all building up to one single critical moment on September 26, 2022.
Now, check out this incredible mismatch. This is a true David versus Goliath story. The DART spacecraft weighed just 579 kilograms, about the same as a small car. Its target, Dimorphos, weighed 5 billion kilograms and was the size of a football stadium. I mean, how could something so tiny possibly hope to move something so gigantic?
Well, the answer wasn't about size or strength. It was all about physics. See, mass is only half of the kinetic energy equation. The other half, the really important half, was velocity.
At the very moment of impact, the DART spacecraft was moving at an almost unimaginable 23,000 kilometers per hour. It was that incredible, blistering speed that was going to transfer enough energy to give that colossal asteroid a tiny but very meaningful shove.
And that's really all they were shooting for. The math showed that if they could hit Dimorphos at that speed, they could change its path by just 1%.
Now, 1% sounds tiny, right? But over the vast distances of space, a 1% change is everything. It's the difference between a direct hit on our planet and a safe flyby.
Okay, so after a 10-month journey and years of planning, this was it, the moment of truth. The whole world was watching, live, as this small, car-sized probe hurtled towards a stadium-sized rock millions and millions of kilometers from home. The live feed from DART's own camera was just breathtaking. You could see Dimorphos getting closer and closer, its rocky, cratered surface filling the entire screen. Until, just like that, the signal went dead. Silence. That silence was the confirmation. Direct hit. You can imagine the scene at NASA Mission Control, just pure joy and relief. History had been made right there. Humanity was no longer defenseless. We had actually done it. We proved we could intercept and change an asteroid's course.
So the big takeaway is this: the experiment was a massive success. We now know for a fact that this kinetic impactor idea doesn't just work on a whiteboard, it works in the real world. It is now a proven tool in our planetary defense toolbox.
But, and this is a big but, this success brings us to a much bigger and honestly more sobering thought. DART was a test on a relatively small target. It was a proof of concept, an absolutely vital first step. But Dimorphos isn't the kind of asteroid that threatens civilization as we know it.
And that is the billion-dollar question we're left with. We've proven we can deflect a bullet, but what happens when the cannonball is headed our way? Is this technique powerful enough to protect us from the next Mount Everest-sized rock hurtling through space? We have officially taken our first step in defending our planet, but the greatest challenges, well, they may still be ahead of us.